today we're going to talk about path integrals. And Burkhard, Militzer, one of the organizers, is going to give the morning sessions and then also the afternoon lab. So we'll just get started.
Well, thank you, David, for the introduction. And I sort of learned many things I'm going to be talking about from you and even stole some slides from you. So David Severly is probably the main proponent of path integral computation when it comes to bosons and fermions. And we will try to cover both of them in this morning's lecture. There are going to be three of them. The first one is about introducing path integrals and how does it allow us to study quantum systems at finite temperature. That's the fundamental difference to all the things you will be hearing for the rest of the school. This is about computing things when excited states are important. So to start out, I would like to quote famous Paul Dirac, who actually said that the fundamental laws necessary for the mathematical treatment for a large part of physics and the whole of chemistry are completely known. It's just too difficult to solve them. And he said this in 1929, and that statement, if you read it carefully, it seems for the mathematical treatment, and this basically means we understand the Schrödinger equation, we understand the Dirac equation, and therefore we can predict the material at any condition in principle. However, he also says that the mathematical formulation is so complex we cannot solve any of these equations. And it's been 80 years almost, and the statement is true. Still true, we do not have methods that allow us to solve these equations. The only modification we can have is basically add one word. And I would say they are too complex to be solved exactly. So if you apply it in the mathematical sense, none of the techniques we've shown to you are mathematically exact, but they are very accurate and but approximate, and still they allow us to predict the materials, the properties of materials at, with high precision that allows us to predict experiments, to compare with experiments, and to give an interpretation and explain things that you cannot directly see in an experiment. So you should see it under these conditions. All of the methods that we talk about have some form of approximation, and you should know where they are, because that helps us to understand the limitations of those methods, and it helps us to think about how to compare one against the other, and it helps us to identify problems that have not been solved. So understanding limitations is very important. So we will be starting out by talking about path integral Monte Carlo for distinguishable particles, and that will mostly be about the zero-point motion of atoms, for example. And then we move on to bosonic systems, which will introduce us to superfluid systems, and then we're going to continue to talk about fermions. Path integral Monte Carlo was actually developed by Feynman to understand superfluid helium, but it turns out that you can now use the same concepts to study fermions at much, much higher temperature. So Feynman was interested about 2 Kelvin problems, and now we're doing millions and hundreds of millions of Kelvin with the same technique. So this afternoon you should get your hands on a path integral code and go through a number of exercises we prepared for you. It's mostly the hydrogen atoms to start out and the hydrogen molecule. And then we show you how to run fermions. And you should see, compare the direct simulations of fermions that exhibit the famous fermion sign problem, and then compare the results with the restricted node approach. And then we move on to talk about a carbon plasma. So until this year, we are not able to run carbon or any heavy nuclei, and we just did it recently with Kevin Driver and published a paper on this, and you should just straight away get the input files and run these calculations for yourself. And then we can move on to talk about the hydrogen plasma, which has fewer electrons, and you can do a few more calculations. So we hope you get through this lab and you sort of understand the main functionality of this one path integral code we're going to give you. So to yesterday we learned we have molecular dynamics simulations, and they basically solve Newton's equations of motion where you have a potential. And they will lead in thermodynamic equilibrium that every particle has 3/2 kBt kinetic energy, which means you do not need to even consider the momentum distribution if you wanted to run these simulations in Monte Carlo. The potential energy is the real thing you would compute, either with molecular dynamics or with Monte Carlo methods. So they are in real time, give you access to real-time information, while Monte Carlo does not. So the remaining of this talk will all about Monte Carlo methods that allow us to study systems in thermal equilibrium. So you learned yesterday how the metropolis algorithm works. You have an initial starting configuration. You pick one particle, you propose a move in a box, for example. Then you have a new configuration. Then you compute the old energy versus the new energy. If you go downhill, then you always accept, and you go uphill with a certain acceptance probability where the energy difference enters and is related to KBT. More importantly, you're actually comparing the probability distribution of the new configuration versus the old configuration. And what I tried to say yesterday in my question for lunchtime, why are these Monte Carlo simulations very similar to the VMC calculations that David Zeppeli also talked about? The principal mechanism is that this Monte Carlo simulation is just an efficient way to solve integrals. And it's for many particle simulation, it's very, very important to have these efficient methods. And they are efficient because they only sample the more likely phase space. They do not sample this phase space where all particles are clustered up here in a small part of your simulation cell where the potential energy is so high that the statistical weight of such a configuration is very small. So Monte Carlo, as a result, is efficient by sampling the relevant space, and it comes at a cost. And the cost is that you cannot determine the entropy or the free energy directly because you're only sampling a subset of the configurations. So what do? You generate this Markov chain, and you basically, rather than calculating an average by solving two integrals, one for the observable, one for the normalization, you're just adding the observations for all these different configurations that you've generated. And importantly, you have to add them multiple times if you have not moved. So now let's use these things to generalize them to solve path integral problems. And the method was developed by Feynman. And let's just start out by real-time path integrals. It starts out with a propagating function g that takes the wave function at time t, and then you integrate over all possible r prime, and you have this propagator that allows us to predict the wave function at some later time t. And the propagator is basically e to the minus delta t h, where h is the Hamiltonian of the system, and here you have appearing an oscillating phase. So in principle this is exact, and you can use it for analytical considerations, but for Monte Carlo or numerical work it's not useful because this oscillating phase makes it very, very difficult to get any reasonable answers out of this. More importantly is the imaginary time path integral formulation, where you replace it by tau. And now the propagator propagates forward where you have a difference in time, but the I is gone, and therefore there's no phase oscillations. As a result, we can predict, we can propagate a state f forward in imaginary time. And if you look at this operator here, it will be with you for the entire week. It's basically, if we rewrite it, it's e to the minus beta h, which beta is the 1 over kBt, the inverse temperature, but it plays the role of imaginary time, how you propagate forward from the left to the right. And it is equivalent or similar to the Boltzmann factor. So if you think about this problem, this will actually weight different quantum mechanical states by projecting out, or by basically saying the lowest energy state get the highest weight as a result. This propagator will also be used in ground state quantum Monte Carlo, where it helps you to project out the ground state in a stochastic fashion. We use it for the path integrals in the following way. So this object that appears here has two arguments. The rho is the density matrix, which you may not be very familiar with. It has two arguments, r and r prime, and this operator is actually the density matrix operator, and you're just representing it here by sticking two arguments r and r prime, and you're representing it in a real space notation, or if you like, in form of giant matrix. We never write it down, but formally that's how you would write it. So the density matrix is the principal object for all pathological work, and it can be obtained in different ways. This is the standard form, but if you know the eigenstates of your system, exactly all the many-body eigenstates for your system, you can actually determine this matrix exactly, and you sum over all those eigenstates, put the Boltzmann factor on here, and you have the first wave function argument with the complex conjugate with the, that enters with the argument r, and then you have the wave function again entering with the argument r prime. And this is sort of useful for a few isolated problems where we know the exact wave functions. Then you can determine the sum analytically and get useful results. Furthermore, if you know the density matrix, you have solved the problem completely. You can compute the trace of this object by having r and r prime, sort of setting r prime equals to r, and you can determine the average for any thermodynamic operator by sticking the operator in front of the density matrix by itself, take the trace of this object, and then normalize it. So once you know the density matrix of the system, the problem is solved. So the problem, of course, is that we do not know these things for many systems. We do know it, however, for free particles. So the one thing we need to understand, how do free particles behave, because we can learn quite a few things about the pathological computation to come. So for free particles, one free particle in a box, these states are known. These are our famous plane waves, e to the minus ikr. And then we have the energy, which is just proportional to k squared. And I sum over all eigenstates, which is an integral over k space, and then normalize it appropriately. If you perform this integration, you basically get the following object where you have lambda is related to mass, and you have the two arguments, r and r prime, are connected by this exponential term that plays a little bit the role of a spring. So if the r and r prime cannot get very far away because they're being pulled back by two effects. First of all, for very massive particles, they're very, very localized, which is shown here by this Gaussian distribution, where I plot r minus r prime on the x-axis, and I plot the magnitude of this density matrix. So if you have a heavy particle, or the particle is at high temperature, which means very small beta, then the particle is very localized. So this is a little bit confusing object, because you may be thinking about particles at high temperature moving very, very fast, and they should get everywhere. That is true, but the particles are classical, and as a result, they're moving fast, but this measures their quantum nature. So even though they're moving very fast, the internal structure, the quantumness, or the delocalization of their wave function is not important. They behave classically, and classical particles are point particles. So there's always a little bit of a quantum effect, and that is determined by, for example, this free particle density matrix. So if you make a particle more massive, the quantum effects disappear, and this function becomes a delta function. It's still moving fast. Similarly, if you increase temperature, this also goes to a delta function. Particles in the real-time sense move fast, but in the quantum sense, the density matrix just tells you the particle is almost classical. So to get the classical limit in this formulation is very simple: either increase temperature or increase mass. At a lower temperature, quantum effects appear, and in particular, when particles are very light, like electrons, we know they're very quantum mechanical, then this function becomes very delocalized. So in principle, free particle density matrix is a Gaussian that we'll be using for quite a few simulation techniques. So a fundamental step towards actually path integrals is the matrix squaring property, which you can write down on a simple sheet of paper. You start with the operator, which is rho equals e to the minus beta h. And you just split it up. You just say beta divided by 2, and here beta over 2. This is obviously an exact relation, and beta is 1 over t. However, it looks simple in operator notation, where these are two operators, but if you write it out in real space, you have to insert a complete set of states, which I labeled R1, and you have to integrate over all intermediate states. When you, for example, want to go from R to R prime, you have to insert this R1 in the middle, just because in operators it doesn't appear, but here, if you write it out in real space, you have to insert one complete set of states. But now we have an object that looks almost identical to the object we started with, except that we have divided beta by 2. So we replace an object that had the imaginary time beta by two objects that had beta over 2. So in the matrix squaring method, you would just multiply these two matrices together, and the integral is just the matrix product, as you can see here. So this is the fundamental step. What we've done is we expressed the density matrix corresponding to imaginary time beta by a product of density matrices of half the imaginary time. And half the imaginary time is twice the temperature. So basically, we replaced a problem at temperature T by an integral with a density matrix of 2T. So this can be done many, many times. Here I've just written one more time, where I split up beta in 4 intervals. In operator notation, I basically have an exponent of 4, and I'm repeating that step. I have to now insert 3 complete sets of states and have something that almost looks like a path integral. Because from R to get to R prime, I have to integrate over all intermediate states R1, R2, R3. I have to make 4 steps, and in those 4 steps, I can go anywhere. So I have to sample over all possible intermediate states going from R to R prime. And I can continue doing this an infinite number of times, and you don't have to, but for example, we have m of those states. So we're breaking imaginary time beta into m intermediate steps, and we call this step size tau, which is beta divided by m, and m can be any integer in principle. We usually use powers of 2, but no, not really. I would just anything will basically work. And this is our time step in imaginary time, similar to the time step you will be using in diffusion Monte Carlo. And this is called the Trotter breakup. It's an exact identity, but now we have m minus 1 steps to go from R to R prime, and these are the intermediate states that have been inserted. You can really go to the limit of m going to infinity, if you like, and then you can actually write, this becomes an exact identity where you do not have to worry about correction terms. There would be normally commutator corrections here, but if the time step is very, very small, you can split the kinetic energy from the potential energy, and that is a key component. At small steps in imaginary time, some of the correlation problems disappear. You're solving a problem at very, very high temperature, where the problem is more classical. And therefore, you can make approximations and that are only valid at high temperature. So we have a good expression for this propagator, just because we can separate the kinetic from the potential energy. So at high temperature, small taus, we know what to do. Then we insert it in this path integral, and by integrating over all those intermediate states, the full quantum mechanical solutions reappears, which we would not have been able to write down analytically. So we traded one problem for the other because we now have to use very heavy computation, but we solved the problem because we can now describe the propagator, which we would not have been able to at lower temperatures, where quantum many-body effects are important. You're now getting away with a problem where we have 2 particle problems, and 3 particles and higher order correlations then reappear when we solve the path integrals.
Excuse me.
Yes?
We don't need to worry about time ordering in this method.
We do need to worry about time.
Ordering.
Time ordering?
Yeah.
So you mean in this particular expression?
This particular exponential.
In the limit of m going to infinity, where you have very small time step, these questions disappear. You do not have to worry.
Eventually, like some kind of continuous picture.
We don't. We will show you. I think in ground state quantum Monte Carlo, you have done that. We use alternative ways to describe this propagator.
So one question. So here you have written as an equal to. So does that mean that when m tends to infinity, the commutator between t and b disappears? Is that
The commutator that you would add here scales to the higher order of tau, and therefore in the limit of tau going to 0, it will get a very low weight. So
Right.
these corrections disappear.
Okay, so that's my point. Is so this is that equation is only valid in the limit of tau equal to 0. So there should be another limit in front of it that will say in the limit tau equal to 0.
Yeah, so I didn't write this very carefully. When I say tau, I'm implying that tau is
it depends
related
on
to
m.
it. So you fix theta, and it depends on m. Yes. So I should have mixed. Yes. One more question.
So when R equals R prime, rho is included in the density of particles at R. When R doesn't equal R prime, how do you interpret that, or do you bother?
No, that's just be careful. If R is equals to R prime, in the pathological picture, that means you are starting at one location R, let's say it's here, and then you have imaginary time. 1, 2, 3, you can do n, you can visit other particles you like, and then you come back, and you have imaginary time 5 seconds, and you have to be back on step. So you are a quantum particle, but you can walk around because you have plenty imaginary time. So now you ask, so this is true. So if you start on R, you end up on R, you can still walk around and have plenty of fun. Secondly, you're asking me, can you really interpret this as a particle being at R? And that is typically difficult because you have a quantum mechanical problem you're solving. So technically, you always have to stick these things on in the proper quantum mechanical formulation where you have the operator times the density matrix and you take the trace. So on the other hand, if you're starting at R and you come back to R, there is a good fraction of time you will be spending at R. So intuitively, you're right, but you're not right in a strict sense. Any other questions? Yes?
When you calculate the exponential, how do you maintain the unitarity property? The exponential should truncate somewhere.
So we do we worry about unitarity? The question is how we guarantee unitarity. I think.
Well, unitarity is only in real time, not in imaginary time.
I think the problem doesn't exist if this is not in imaginary time. So you don't have to worry about it.
When things decay to the ground, unitarity would be not
But
conserved.
still there is a time, suppose you see the same picture with the time,
Yes.
then what happens with the
Then you get, then this propagator is very complicated, and you get, at any temperature, you get phase oscillations. And then what happens if you do that for many, many steps, as you change R1, for example, you go through a series of phases, and then you have to basically, a complex, you have to average over a complex function. And then let's say you go to R2, you just went through all possible states of R1, and now you're going through R2, and you have again a slew of different phase factors. So it becomes an intractable problem. Analytically it's all fine, but basically...
Actually, analytically, it's not. I mean,
analytically it should be difficult because you have to truncate the exponentially.
yeah.
So you will lose the unitarity in every step. That's what
Well, if you can solve it in the harmonic approximation, then you can solve it. Otherwise, it's not all fine if you can't solve the integral. Yeah, so that's, the truncation is dangerous.
But imaginary time things are much nicer.
Okay.
But they're not unitary at all.
Okay, thank you. All right, so the simplest way to actually do that is to write it down in a primitive formulation where you just have to describe the action. So now we're introducing the weight of the path, where you sort of, you try to weight different paths compared to other paths, for example, and that's typically done as the action. So what basically happens, the weight of the path has two components, one arising from the kinetic energy, and that you can write down as the deviation between two adjacent slices. So what happens, just let's view this picture, we'll use it multiple times. We basically plot imaginary time on the vertical axis, and on the horizontal axis real space. So we're giving up on multiple dimensions, we just say x for this purpose. If you would plot it in x and y, you would have these ring polymers. Here we have a very heavy particle, so if you plot it in this imaginary time world line picture, then you would basically, it's very localized, but still fluctuates. And then you have a more quantum particle that has a lower mass, and therefore that fluctuates further away from its starting point. So the potential energy acts at every time slice. So rather, a classical simulation would just have one point in this picture, and the particles would just be points. But now we have path, and they interact at the same time slice. So there's no interaction when it comes to potential energy across time slices at different imaginary time arguments. The potential energy is, if you like, in this most primitive formulation, just a diagonal or a same time contribution to the action of your path that arises here. So if particles get very close to each other and you have a resulting potential, repulsive potential, the function would get very large, and such path would be rejected. So now we have the second term appearing that links the two slices. We have R1 to R12, and you normalize it by, you divide by the lambda, which is related to mass, and imaginary time. That's our time step appearing here. If you make very large steps in imaginary time, the path and these beads can get further away from each other. And if you want to make a very accurate calculation, you typically need smaller time steps. And then these time steps can't really get far away from each other. So this is what we call the link action, or the kinetic action, if you like, and this is the potential action. So this links adjacent beads and makes sure that paths that are heavy stay localized, almost classical, and quantum particles actually can get away. They can really travel in imaginary time and explore the quantum nature of the system, and they will ultimately sample your ground state wave function. So here we have the potential energy that is similar to your classical Monte Carlo simulation. So these are the two things you should keep in mind. We have replaced classical particles by path, and they are wobbly objects. And at low temperature, these wobbly objects will sample sort of your ground state wave function. So the analogy to ground state quantum Monte Carlo, which we will label diffusion Monte Carlo, is where you let the number of slices go to infinity. Now we're doing it differently. I didn't say this carefully. Now we fix the time step and make an infinite number of steps. And we do not worry about closing those paths. We just keep walking forever, projecting out the ground state using this operator. In finite temperature formulation, we have a finite number of steps. And the paths are in most simulations ring polymers. They have to go back to where we are, except when we want to compute things like the momentum distribution. So there's a simple picture, if you like. You should keep in mind that the paths that are heavy, given by the red lines, are very thick, and the thermal de Broglie wavelength, if you have imaginary time, they can't get very far away from where they started from. And now we have electron path, for example. They're very light, and they have, as a result, a small beta factor, and therefore this capital thermal de Broglie wavelength, which incorporates the temperature or the beta factor here and mass, determines that they can really wander off in imaginary time. So is this a natural phenomenon? I'm inclined to say yes, as you can see in this picture here. What basically means heavier objects don't travel as fast. So what do you need to write your own path-integral code? So I thought I would describe the most simple procedure we'd need to write your own code. And maybe we'll just, a few things become clearer then. So to start out, you will describe what is the state of your system. What was S yesterday in David's lecture, how many coordinates do we have? Well, first of all, we now have path, which means we have m time steps. So whatever in your classical simulation was a system of 3 dimensions with n particles has now been replicated by a whole path where you have another imaginary time dimension. So you have an additional factor of m, so you have to allocate memory accordingly if you like, and you have to start your simulation somehow. So what we typically do is you put your particles on a lattice, and then you just make all those imaginary time arguments the same. So not as I've drawn here, they just put every bead on your path on the same location. Then they would, in the real XY picture, they would all be in one location. And in this world line picture, they would all be at the same location. You would start with like rods in imaginary time. They all behave perfectly classical. So then you have to tell your code how you want to move. So the first thing is you pick one bead out of those imaginary time slices. You pick anything you want. You pick this bead and you sample a little bit real space window, which was our box in real space. And we pick up this bead and we basically propose a new location. So I'm just saying you do this uniformly in the box as we've said yesterday. And now you basically compute the difference in the action. And you have two components to worry about, the kinetic action and the potential action. So if you're putting this bead over here, you're introducing a huge kinetic action. These strings have to be stretched very much, so that will most likely be rejected. Similarly, if you run into another particle, this will also be rejected. But we will not worry about this. Let's say we have a way, we pick a reasonable size imaginary real-time window, real space window, and then we accept or reject by saying if the action goes down, we accept, and if it goes uphill, then we accept with this probability. So that's the simplest but very inefficient way you can run your path-integral code. The other thing you may want to worry about is the following fact. If your particle is very heavy, then it doesn't fluctuate very much in imaginary time. So it's almost like a classical particle. So you will never be able to move one bead very far because you basically had to stretch the kinetic action beyond anything that would work. As a result, if you are just using these single bead moves, you can never move a classical particle because a single bead will always be held back by its neighboring beads. So what you have to do is take a classical move. You basically say, well, if this path that's in front of you, you just get the whole path and you just put it somewhere else. So that would be the equivalent of a classical move where you pick up the whole polymer and you put it somewhere else. So that's basically what we would do here. You take the whole polymer and shift it to a different location. And in this case, the kinetic action has not changed because we have not changed the internal structure of the path. You just have to compute the potential action. But this has changed at every time slice. So such a move where you pick up the whole polymer moves a lot of beads, which is good. But it's also expensive because you have to recompute the potential action of all slices. But for protons, which we sometimes call heavier particles because they're heavier than the electrons, these are the only efficient moves that really change anything in your system. So then you do this over and over and over again. You want to have moves that are quantum moves that change the internal structure of the path. And you want to have some classical moves for particles that are very, very heavy. So what does it really buy us? Well, what you should think about it is always good to remember what you learned in the second physics class. You go back to harmonic oscillator. In quantum mechanics, you know its ground states. You can therefore, and also the excited states, you can determine its density matrix analytically. So now let's just see what would happen if we run a classical simulation. So a classical simulation, and the particle would move around in this harmonic potential well. Let's just to see the difference when we go to t equals 0. We just run our classical simulation at lower and lower temperature. In the classical simulation, the classical ground state is really at the center of the well at the minimum state. So the classical particle would sit at the bottom of the well and not do anything. So not so the path-integral Monte Carlo simulation, because they can reproduce the exact ground state, which is 1/2 h bar omega, and that arises from the following fact. Even in the ground state, these paths are wobbly objects, and they will never sit in the, or almost never sit. They will never be glued to the grounds of the system. They will be moving around. And it's the kinetic action that drives their quantum motion. So you run your path integral on this problem, you will very nicely reproduce the ground state. Effectively, you do not have to, because the result is known analytically. There's no real need to run a computer simulation unless you want to test your code. So we know how we move the beads in the system. We have a system where you can test our simulations. We just have to compute a few things. So I only said how we move particles. So we move them according to this action term. It has these two kinetic and potential action items. And now we have to calculate, for example, the kinetic energy and the potential energy. In classical simulations, we did not worry about the kinetic energy because it was 3/2 kBt. That's not correct for a basically a system, a quantum system that has interactions basically. And we already know from the harmonic oscillator it is 3/2 kBt classically, but not in the quantum simulations. So we have to calculate the kinetic energy. So there's a term that appears that measures how far the adjacent beads really got away, and then that relates in the classical limit, this term, both of those lead to 3/2 kBt, but in the quantum simulations you get the exact kinetic energy for this quantum system. So the potential energy is similar to the action. I think I made a mistake. This should be a 1/2 here. So you just average the potential energy for all those imaginary time slices, and that's your average potential energy. So the tau is wrong, should be 1/2.
One question.
Yeah.
So I noticed that in this formulation, when you made the trotter expansion, right, you kept the kinetic energy in the action.
Yes.
But you could have also put another, resolution of identity between the kinetic and the potential, so that you will have an analytical expression for just the kinetic energy propagator.
Yes, so you're asking effectively if there's different ways of introducing propagators and writing down a different action. Yes. And
so my point was, is there any benefit of doing one versus the other in terms of implementation or?
Yes. So I will talk about it actually when I come, this is other slides. Basically, I'm just trying to say the most simple fact. So yes, the simple message is this is the most primitive action that you can write down. It helps us to understand things. But computationally, it's not the most efficient way unless you don't know how this potential looks like. The potential, for example, comes out of a complicated DFT calculation. We have no knowledge where this is derived. This is probably what you would be doing. So, but however, in many applications, if this is the Coulomb potential, you can do much, much better. So the quick answer is we will come to that problem in a few slides. We have to do much better to write down a more accurate action, and that helps us to make bigger steps in imaginary time. With a lousy action, you have to make very small steps, but with a more accurate action, you can save time. And it's exactly these tricks will make real applications possible. So yes, so the next chapter is basically improving the sampling efficiency. And it comes back to the following fact. Initially, I just told you, you just pick up this one bead and or you just had this original location here, or you have this bead here, and you're trying to decide where you put it. And this comes back to how do you move particles efficiently in Monte Carlo simulations. In classical simulations, there are some tricks you can play, but you can probably get away with a simple box. That just usually works. With path integrals, it's essential to make this process efficient. And if you have the non-interacting case, you can actually determine what the distribution of beads should look like. So you know the answer if you ignore the potential energy. You should know you have the free particle operator, which is a Gaussian, which is a string that sort of a spring term that connects these two, and then another spring here. So most likely, this bead you're trying to find a new location for will be at the midpoint. And there's also an exponential or a Gaussian bell-shaped curve that determines its probability function in this imaginary time slice. So you have two springs connecting the bead to the slice above and below, and as a result, if you ignore potential effects, you can write down the exact distribution. So if I know the exact distribution, I can do tricks. I can sample from it. If I know it analytically, I can throw beads or propose beads according to this distribution because it's a Gaussian function. And you can write down this probability function for this function for the new location of Ri by having the free particle operator from this location here Ri minus 1 to R in imaginary time t, and then you have the same function here where you describe the link to the upper particles. You keep those two fixed, but this is a function of Ri that determines the optimal sampling distribution for determining this new Ri. So this function needs to be normalized, and the normalization just arrives for the propagator that gets you from I minus 1 to I plus 1. It's one matrix squaring property that is the normalization of this function. So now I know the best possible way to predict the new location for this one bead, and now I can correct this, this acceptance procedure. I have a new way by generating points according to this Gaussian distribution. The maximum is at the center, but now I'm basically proposing so states with a probability distribution that falls off according to this free particle propagator. So now I'm proposing states that are next to this midpoint much more likely than states further away. So this here I have to compensate for, and that arises in this acceptance probability where the if you propose states more likely, you have to divide out how you made that move basically by going from the old state to the new state and then the reverse probability. So what this means is by proposing the exact solution, you can actually get this factor to 1. If you only have if you have no potential terms, you only have kinetic action in your system, you're sampling with the exact distribution you're expecting, you have no rejections. That's the important point. If you know how you should sample, the acceptance in your probability in Monte Carlo will be 100%. In reality, we always have some interactions. We cannot write down easily these propagators here, so we'll get some rejections from the potential energy, but we're sampling the kinetic problem exactly that leads us to a very high efficiency. The second thing, this is one trick. We're using the kinetic action to sample efficiently. The other trick is to use MultiSlice Moves. So it should be a Levy construction I'm proposing here. We want to cut out a large section of this path. Not just moving a little bit because we would be limited by the two adjacent beats. We're not moving. We're just keeping this one fixed and this one. And we want to regrow this whole section of the path in order to be able to move it really far away rather than just basically moving a little bit. We're now sort of cutting away a larger section in imaginary time to allow for more efficient moves. So you have two ways of doing that. So the Levy construction just tells us we pick the first bead. So we just go in one direction, we fix at 0, and we want to end up at 8. So we are fixing those two locations, and now we're just proposing a new bead for imaginary time 1, and that is given by the free particle propagator we just described. So we have the imaginary time propagator, which is our free particle density matrix, moving from slice 0 to 1, and from 1 to 8, and this is my sampling probability for picking this new bead at location 1. Once I've done that, I'm basically picking the second slice. I've fixed this slice now after choosing it. Now I'm picking my second slide here according to the link between slice 1 and 2, and I have 6 imaginary, a distance of 6 imaginary time steps left. That basically gives us the probability distribution for selecting particle R2, and you have to end up at particle 8. So this initially will be a very loose constraint because you have so much imaginary time left. You can go anywhere. You just have to be back at slice 8 at this location, and you have to normalize it. So this constraint becomes stronger and stronger as we march along towards the final slice. So if you keep doing that, we will basically regenerate this path in forward in time, and finally, really, the constraint by ending up at slice 8 becomes stronger and stronger. So this is one way, the Levy construction, where you regrow this path according to the kinetic action. So at the end, you have your whole path generated. The acceptance probability is 1 because you use the kinetic action exactly. And now you have to evaluate all those potential energies at these other time slices. So this will lead to a giant accept or reject step. So if you take a large imaginary time window, the path you've generated will not know that there are other particles around. So they will run into each other, which may lead to a huge rejection step. So if you make that window too large, and you're sampling with the free particle density matrix, you will get huge rejections. Just because particles will run into each other, because this method is blind to interactions, unless you change this propagator. So this is one way, this is the Levy construction. There is a more efficient way, and that relates, is the bisection method, or you build a Brownian bridge in a similar way. You again fix those two slices, but you're picking your midpoint first. So the midpoint gets picked between 4 imaginary time slices. You're far away 4 steps from the final slice, and you're 4 steps away from your initial slice. So you have a Gaussian that is basically larger width according to, well, 2 time slices, or 4 times tau, or 8 times 5, depending how you define it. But definitely you have a large sort of window. The Gaussian will be more spread out just because you have a larger imaginary time distance to cover. So this, you have more freedom of selecting this midpoint, which helps us to make bigger steps in imaginary time. So we pick this initial point, and then we have to fill in slices 6 and 2 again using the free particle propagator that links slice 4 with 8 and 4 with 0, and we have 2 new points fixed. So then we fill in the remaining gaps, and we have a new path being generated. So far, this will be this similar path we have generated. If you just use the kinetic action, you can use the Levy construction, or you can use this bisection method. The efficiency of your algorithm will be the same. The argument to be made for this bisection is actually, there's a way you can reject unlikely moves already when you just pick the midpoint. That's the point where it basically this becomes more efficient. So we use the bisection method exclusively in the codes that we run. Yes? So if there is interaction between momentum and position, that depends on your Hamiltonian. So do you have a Hamiltonian where you have a term that we couple momentum and position? Yeah, then the whole thing may actually break down. Then I think you can potentially, well, if you have unusual Hamiltonians like magnetic fields or something, you can easily generate propagators that have an oscillating phase. So it's really not trivial. So what I'm saying here is applies to regular real space potentials. So if you want to go beyond that, there are non-local potentials, then you have to rethink the foundations of what I'm saying. Any other questions? Yes?
I wonder why you do not include potential action in the intermediate stage.
Yes, you can do that, and the question is, David developed a method where you use these things, and for example, if there are 2 particles nearby, you preferentially shift this Gaussian away from the other particle. Yes, so this is possible. The difficulty is the following. To choose this point, you need to determine this function analytically. You have to be able to integrate it out, to determine its normalization. So you have to be able to solve this integral, and that's difficult if you have too many particles around. So it's just because you want to determine the sampling distribution is given by this free particle density matrix, and to put interaction effects in a meaningful way in here is not simple. So that's where it arises. It's possible to do that, but it's not trivial. Because you have to be integrally determine this propagator. But in principle, this is one for liquid helium. This is exactly the crux where it's hard to do this in an efficient way if the system is very dense. You know, in a plasma or in a low-density system, all these things do not matter too much. If you get in very confined systems where particles are very strongly interacting, they're constantly running against each other, this becomes a real difficulty.
I have one more question. Could you please comment on how the quantumness of particle affects the efficiency of this bisection algorithm and the three-particle sampling method?
Yes, so how does the quantumness of the particle affect the efficiency of the method? And if you define quantumness in the simple-minded picture of saying it has kinetic energy, then everything is fine, because we're using the exact sampling method for a non-interacting system, non-interacting particle, regardless of the interaction. So if the system, it can have any mass, it can have any temperature, it can be as quantum mechanical as you want, this will be the exact way, unless potential comes in. So if you have a potential interaction and you're now saying, well, this affects, the potential is the problem because we're not considering this. So there could be combinations where you have the interactions and the quantumness of the particle lead to a new distribution that we're not sampling well, then this could be a problem. But in principle, the quantumness primarily affects the kinetic energy, and we're solving this exactly. So I would say we always blame the potential rather than the quantumness. Any other questions?
It is difficult to generalize to the field integral.
To the field integral? What do you mean?
I mean, so we just do not do the real space path integral, but for field integral.
I'm not sure what you mean real time. You're doing real space and imaginary time. So there's all work.
Quantization.
Yes, after
Like
that,
a lattice model or
I think that cannot be done in this approach, right?
Well, some lattice models can be done. I mean, if you do a Hubbard model, there's something called world line Monte Carlo they use.
So,
or something like the SSE algorithm is very similar.
okay.
But there are lattice models that can't be done also. But
Thank you, David. Okay, so to conclude, if we use the bisection method, we can reject some of those states, and therefore we gain a significant factor in efficiency. So what we want to improve upon is coming back to more efficient actions that allows us to describe this propagator from step 1 to step 2 more accurately, and therefore it allows us to make bigger steps in imaginary time, and therefore reduce the number of slices in our simulations and have an overall more efficient simulation. So I'm just picked one of the possible methods. In principle, there are lots of analytical techniques. I pick one that's very robust, and we've implemented in all the codes, and it's actually relatively simple to understand. So the simple formulation we have, we want to determine this propagator from R to R prime, and that is a way to introducing our action. The simplest way we already described, this is our primitive action having those two terms. So now I'm talking about the pair action method to improve upon these things. And the argument is the following. If you have a two-particle problem, you can solve this exactly in almost all cases. So if you have a two-particle problem, the method can be done. So now I'm sort of proposing my many-body system that's Coulomb, that has many interactions. I'm just using it in the following way. I can separate the system that has many particles by having an interacting piece from the action. And I have the free particle propagator where I basically just take out the free particle propagator for every particle in the system. I just remove the ideal term. This is like taking away the kinetic energy from the total energy of a system. So you're left with everything else, which is our interaction action. And now this is exact. You just remove this kinetic energy term. And now we make an approximation, and that's the following. We have a global action where every particle interacts with every other particle, and we're approximating this as a sum of two particle problems. So with the kinetic, we just have the potential action, this is trivial. But if you have if you have to talk about the potential, this is exact. But now we have an action where quantum effects do come in, and they are different between the many-body system, which we do not know, and the two-body system. So we're proposing the following approximation. We're solving all those two-body problems exactly. So you have a proton and an electron. We're summing over all states of the hydrogen atoms. We're sticking this in our action, and then we solve the two-body hydrogen atom exactly. And therefore, we can do any step size in imaginary time. We start with the exact solution of a hydrogen atom, or the exact solution between two interacting electrons, or with two interacting protons. So this is a way of approximating this. We still need a path integrals because we do not capture many-body interactions. But we're starting with a solution of the two-body problem, and it allows us, we have to then put the one factor we took out back in here. So we're basically describing the many-body action as an approximation where we have all these two-body terms. And we just have to remove the kinetic energy, otherwise it would appear multiple times. So the way you think about it is you have all particles interacting with each other, and we're basically decomposing the system into two-body problems which we solve exactly. That's the trick. And it will helps us to be much better than the primitive action up here, because these terms will now be coupled and represented more accurately. So how, yes?
So here, Rij is the distance, interparticle distance?
Yes, exactly.
So then the angular coordinate is integrated out analytically, is that?
Sorry, what's under?
The angular coordinate is integrated out analytically in that expression?
Well, yes and no. So in principle, we do have the angular part tabulated. So what happens is we solve this two-body problem, put in a giant table, and then there is an angular part, and that will be taken care of in the following way. Usually all the potentials are just depending on the magnitude of the separation. So there is no angular dependence, but if you have a path angle, there is an angular dependence. So what this means is we tabulate this non-angular part, which is the radial component, and we do have a correction to capture that angular part, which we call the off-diagonal action. Yes?
Well, I think those are supposed to be vectors there, Rij. Those are actually vectors there.
They are not interparticle distances, they are vectors.
They're relative distances, but vectors. Yeah.
Okay.
So it's Ri minus Rj.
Yeah.
Yes, so in principle this still captures vectors, but in practice we do exactly what I said. We first of all cover the non-angular part and then we correct for it. So how do we determine this pair action? How do we solve a two-body problem? So there's three principal ways. And the first one is we use the definition of this density matrix where we sum over eigenstates. And for hydrogen atoms we consider the bound states as well as the excited states. They're all known analytically. So we just have to sum this all once, store it on an efficient table, and then in our many-body calculations we just look up the action in those tables. So it's just a way of solving a two-body problem. So this is the sum over eigenstates method, and I use the method that Roy Pollock published where he just basically wrote down the expressions for all those Coulomb wave functions. The other way, if you're not fortunate enough that someone for you has already solved all the eigenstates for your potential, if you do not have a Coulomb potential, then you may be out of luck. Nobody has solved this exactly. You have to do something else. So you have the matrix squaring method, which we used for good numbers of years, where we just use the matrix squaring technique to start out at very high temperature and square, I don't know, 10 times, and then tabulate that result. And therefore, we have an effective solution to the two-body problem before we actually start the many-body simulation. So we're using we do this many times, and we're effectively solving a path angle with two particles before we actually start. And again, write it out in a table for efficient interpolation later on. I moved away from this a little bit. I use the Feynman-Katz formula now, which is basically very robust and very simple, and it's on the next slide. The only problem is it cannot solve systems for potentials that have a negative singularity. So for this Feynman-Katz method, it's the following. So we want to know what's the action of a path that starts at R and comes back to R prime. And I'm now trying to do this in this two-body sense, where I just have one potential as a function of R, and I generate path according to the free particle distribution. So I pretend my particles are free particles, and the propagator is just a kinetic action. I can generate those paths efficiently, and I just sample what is the potential along this path. And I generate all possible paths over this from R to R prime, for example. And by sampling over this, I measure the full potential action. So this is called the Feynman-Katz method, where you use the free particle propagator from R back to R, and you allow for all the intermediate steps to sample the quantum nature of your system. And it can be done very efficiently. You again write tables, and what they include is basically you have the path measured. They just include, paths are fuzzy, and as a result they measure a little bit more repulsive potentials, but they also measure a little bit less repulsive parts of your potential, and therefore the action then arises. You can do this at different points in space and then write a giant table. And the result is very simple to understand. If you have the action here and you divide by beta, at large R, all those action items will converge to the 1 over R potential. So at large R, the fuzziness of your path is really not important. So therefore, they behave like classical particles, and classical particles interact via the potential. So our action always converges to the classical result at large distances and small beta, of course. And if you come now closer to the Coulomb singularity, things are different. So as a result, we have the cusp condition that we have to satisfy that arises comes out of this method automatically, and you get a deviation from the potential. And that's very important. So a quantum particle will sort of occupy quantum states, and as a result, you get the cusp condition, and the action does not go to infinity. A classical particle will fall into the potential well of a proton, for example. If you have a classical electron, it will fall into your potential well of a proton you provide. And this means classical simulations for a hydrogen plasma with protons and electrons at any temperature will be unstable. So path integrals just solve this problem at this level by the cusp condition arises properly, and you just have to build this Feynman-Katz formalism. And the problem is solved. So this fundamental thing in plasma physics just comes out naturally and will be very efficiently solved. So this sort of concludes what I wanted to say about the fundamentals, how you run or write your path integral code for distinguishable particles. I want to talk a little about one or two applications, but if there are questions to the methods, you should ask them now. Yes, Nick.
Did any of this, are you using like the Oppenheimer approximation for the nuclei also quantum particles, or are you just treating the electrons?
Yeah, we've not yet talked about the Born-Oppenheimer approximation, and I will just give you a few examples in a second. So if you Born-Oppenheimer approximation typically means the electrons are much lighter than your protons, and therefore they can, you can fix the position of a proton and solve the electronic problem. Or more strictly, you can say you make your proton classically and solve the problem electronically. So far, the path integrals include all those effects. We've not made the Born-Hauptmann approximation, but we've not yet talked about the distant difference between electrons and protons. So far, that's one of the applications I'm going to describe now. Yes? Any other questions? Yeah?
Be the role of periodic boundary conditions if you're doing like a solid or something?
So at the moment, what we do, there's no principal problem. If you have in classical simulations, you have periodic boundary conditions and you introduce the Ewald sum, for example. In path, it's exactly the same. So you also have the Ewald construction to deal with long-range forces, and we do it exactly the same. So there's no fundamental difference. The one thing that arises, the quantum effects are important at small r, but not at large r. For bosons, periodic boundary conditions are very important, and they lead to superfluidity. So then it's very different. For fermions, you have to worry about your nodes, and you may want to construct your nodes that are periodic, so things do arise. But on this level, for distinguishable particle, it doesn't really matter. Yes?
Do you use the same sampling methods with these interactions as you did with the simpler actions?
Yes. Do I use the same sampling methods for free particles and for particles that are actually interacting? And the answer is that...
With the new actions?
Yes. So with the new action, yes, I'm using the free particle sampling methods with the new actions. And then this replaces my potential action. So what it usually does is you have this complicated action, you're ignoring it when you sample the path, and then you sample the path according to a free particle action, and then you remove that part when you accept or reject. So this works very nicely with the initial free particle sampling method. So just to say what we really do, for all simulations, we use the free particle sampling method. And the only reason why David has done it is for helium. He has a way of shifting these centers of Gaussians. But I don't even use it for the plasma simulations and for the hydrogen simulations that I've used. We always use free particle sampling. It's just because we could shift, we could improve at this point, but it's not the step that's limiting us at the moment. Yes.
So in this, how do you eventually extract the pair potential? Because in the equation it only has the average and the integrate versus the ground state. So does that take?
Okay, so the question is how do we actually extract the potential, because there's this average here. So average doesn't mean ground state. Average just means average. So what I really do in this code, when you give me an arbitrary potential which you just wrote down, you sketched something on a sheet of paper, I will ask you for a spline file. I take the spline, put it in the Feynman Katz code, and I generate millions of those free particle paths. And then I will, over this million paths, I will average the potential that they sampled here. So they wiggle around about what you've written down, what you gave me in the file. I just measure what was the action along this path that I generated. And I write this number to a file. So that means at this location at 1.3, I measured what was the surrounding of the potential you gave me. What's the average potential energy for a path? And I write it to disk. So they don't have to do this in a many-body simulation. So millions of paths, you just average it. Yes?
So is it possible to get one particle and two particle reduced density matrices from this approach?
Yes, so one particle reduced density matrix is related to the momentum distribution. We've done it for distinguishable particles, for bosons and fermions. Two particle reduced density matrix is also an object is related to open path. And I think I tried to work on something to compute natural orbitals, and I have to say I failed miserably. So in principle, it's not a method that you can have two simulations with open path, but we do not have a good way to extract useful information, because it becomes two open ends is something that has a lot of rational degrees of freedom, and then what do you do with it? That's the problem. Yes, we can compute them, but we don't have a good application to really apply it to something. There was one other question. Yes, Nick.
Just trying to make some connections to what we learned yesterday. So is so each bead on your polymer is a 3n dimensional object. And
Yes.
Each Monte Carlo walker would have at least one polymer.
No, that's different. So basically, you're right when you say that each bead has 3n coordinates, and each bead is the instantaneous state. So hang on, each walker has 3n coordinates. So a walker is a whole line in this picture that I've shown you. So the walker walks forward in time, which means in this one step which we had here, so let's go back to this. So one walker carries the whole information of one bead and steps forward in time. These things have to be closed, but the walker keeps walking forever. That's the connection. All right, so let's go back to the point where I was and then talk about a few applications. And now we say, well, this is a finite temperature method. What I learned in solid state physics, if the solid's in the ground state, the simplest excitations are phonons. So should you really be using path integral Monte Carlo when you go back and talk about phonons? You tell your advisor, I just went to that school and now I can compute phonons with path integrals. Should you do that? Well, the argument maybe you should be doing this. It may delay your graduation day by a year or something, but in principle, it's not always the best method. And the most fundamental thing is, with phonons, you assume that the simplest excitations are harmonic vibrations of your lattice. So the question is harmonic. So if you know that this is reasonably exact or reasonably accurate for your system, you can generate a more efficient algorithm. So computing phonons, if you make this approximation, you basically are much more efficient than you would be with a path integral Monte Carlo simulation. So let's just see what phonons are. If you have a lattice, then there are certain eigenmodes how a CO2 molecule vibrates, for example, and you can measure these things in experiment. If you do a phonon calculation, you basically determine what is the energy landscape of around the ground state location of an atom. You're making the assumption that every atom sits in a harmonic well, and you're just computing the force constant or the Hessian matrix around this equilibrium location of your atom. So this is very efficient, and it will give you the vibrational states of your system. It's very important. Path integrals will never give you individual eigenstates. What we find in this case, you get the actual eigenstates, as I've just shown, how the molecules are bouncing back and forth. You will never be able to extract the eigenstates in the formulation as we know in path integrals. But you will get the energy from path integrals. In this case, if this is reasonably accurate, the path integral Monte Carlo simulation will give you the same energy and the same kinetic potential terms, if you like, as your harmonic approximation. But here you get the eigenstates, and this will be much more efficient than running a path integral code as a result. So yes, the answer is you should not do phonons if you have a solid and the solid is harmonic, because this is more efficient. So then, what about zero-point motion? And this is one application of path integrals, which we do not teach in this school, but there are applications where you run a DFT code, and rather than having classical nuclei, for every nucleus you have a path, and that samples the zero-point motion of your nuclei, like hydrogen, for example. In one application, there is the group Tuckerman and Dominic Marks. They have the CP2K code, where you just have, rather than doing one DFT calculation, you're doing 16 or 32 DFT calculations, and you do the primitive action, because you do not know how this potential looks like, although one could do better than they do at the moment, I would claim. And they can measure things like what are the quantum effects in water. So if you assume DFT is perfect for the electrons, which is not true, but it's a good assumption in many cases, classically you would, for example, see you have a sort of a big peak in your distribution in this in these charged water complexes. In quantumness, they would actually be more spread out. So in classical simulation, your particle sits in the ground state at t equals 0. If you run it at finite temperature, the classical particle would move around. This is what this distribution shows. But now, if you have a quantum nuclei, you see quantum effects in that motion. So path integrals is probably the only method that can get you these zero-point motion effects if the system is not harmonic. So that's why this is a valid application.
All the nuclei are quantum mechanical?
All the nuclei are quantum mechanically. They show this here, for example. If you have a classical simulation, they still move around because, well, this is the oxygens here, and these are the hydrogens. And they move around because you have a classical potential and the temperature is non-zero. Here they move around more because they're quantum particles. This is the quantum simulation, this is the classical simulation. They still make the oxygens quantum, but the effect is negligible. You would get away by making them classical, but the expense is the same, so it doesn't matter.
But okay, so if the entire, so the nuclei is, all the nuclei are quantum mechanical,
Yes.
then how they, then I don't understand the density plot that, from the previous slide, because how they include, how they separate out the overall translation and the rotation of the molecule.
They don't. So you're asking two things. They just plot density distributions. One comes out of the classic simulation and one comes out of the quantum simulation. The quantum simulations, you have quantum effects and temperature. In one you have just temperature. And these are the differences. And
Right. So can you go back to the previous slide for a second? So even for the quantum motion, for the quantum case, right, if all the nuclei are doing free rotation in space, I should expect a uniform density.
no, I think this is special. This is special. This is reduced coordinates. And what basically happens in these complexes, you have two oxygen atoms and you have a hydrogen that's weakly bonded, either hydrogen bonded or covalently bonded to both oxygens. And now you're looking what happens to this one hydrogen. It's an unusual situation. So they picked this because they knew quantum effects would be large. So now they're asking what happens in the classical nuclei with what happens to a quantum nuclei. So you have to read this carefully to interpret what these distributions mean. Yes?
What are the axes on the bottom there?
Yes, okay. So the axes in the atoms are the distances between the two oxygen atoms, and these are the distances, the difference between the two axes from the hydrogen atom. So this can only become clear if you read the paper or you go to this picture. So they have, this is H5O2, they have an oxygen sitting here and you have hydrogens on the back. You have a covalent or a hydrogen bond, that depends on the geometry. Oxygen, hydrogen, oxygen. The plot means the difference between the two oxygens was one axis and the difference between this distance and this distance was the other one. So this is just a way of simplifying, maximizing quantum effects. Just see the effect. Okay, so I'm probably way over time. So I'm going to just say a few things about the Wigner crystal and then move on. So another application, some of you actually do work on the Wigner crystal. So I want to just say a few things about the simulation. The Wigner crystal is a simulation of a system of similarly charged particles. They are quantum or classical. You can have a system of electrons that interact, or you have a system of protons, which is if you compress hydrogen to very high density, the electrons become so screened that they leave the picture. So the Wigner crystal is a system of just one type of charge in front of a neutralizing background. There's one component plasma, if you like, that's either quantum or classical, and interacts with a potential, either 1 over R or you add some screening, and it may be the high density phase of hydrogen. At least that's one application. So that's at least, we have a system that interacts with a Coulomb potential, just one type of charge. And what basically the result is here of these simple simulations using path integrals for that system of protons or electrons is the following. So we're plotting the energy as a function of temperature. And in the high temperature limit, all particles will be classical. So you have the blue line of sort of our classical simulations, and the red are the Pathological simulations for the same systems. So if they approach the same behavior. At high temperature, the quantum nature of the particles is not important. So classical and Pathological simulations follow the same trend, approach each other. In the high temperature limit, you can produce the hypernetted chain calculation that's typical for plasma. So at low temperature, we see a big difference between the result of Pathological and the result of classical simulations. Does anybody know where this comes from? Why do we have a big deviation at low temperature between Pathological and classical Monte Carlo? The quantum nature, yes, and what's precisely?
And the variable is important in the quantum nature.
So the quantum, so basically it's the quantum nature. This is effectively the 0-point motion of your nuclei. That's this difference. So a classical simulation goes to 0, a quantum simulation does not. You have the 0-point effects here. So if you blow this difference up a little bit, you have melting of your classical simulation. You also have melting in your quantum simulation. So Pathological will, you can also study melting. You can study the effect, the difference between the classical and the quantum melting temperature, if you like. And you can also come back to the harmonic approximation. So if you plot the harmonic approximation here, and it does not fully agree with the Pathological result at low temperature. So even at t equals 0, there's a difference between the harmonic approximation and the Pathological results. So where could that be coming from? Any suggestions? Yes, exactly. Well, this is, if it says harmonic approximation, then there may be some unharmonic effects being left out. And that's the result here. Hydrogen atoms are relatively weak, so they relatively light, so they probe particles in the unharmonic part of the potential, and as a result you get difference. So what you should appreciate is that Pathological, even for distinguishable particles, sample the full many-body simulation. You get all the unharmonic effects. It's very expensive, but it's something, it solves a real quantum problem exactly, besides bosonic and fermionic effects. But this is amazing. So this is not trivial to do analytically. So I would stop with the distinguishable lecture, and do you have any questions?
Yeah. So what are the error bars here?
What are the error bars here? So the error bars are smaller than the size of the symbols. So typically, if the curves are smooth, you have some confidence. So we block the similar, like you heard Lester, that you have a blocking analysis for your error bars. We do the same thing for Pathological Monte Carlo. Okay, so shall we have a short break? Well, how about, sorry?
It's been an hour and 20 minutes, so I guess it's time to get up at least.
Okay, so how about we meet here again short after, it's like 5-7 minutes, I would say.
You mean just 5? Just
Yeah, 5 minutes.
10:30 or something?
Yeah, 10:30 plus.
Are you finished up tonight?
Yeah. Oh, yes.